The title of this presentation is Upper Bounding System of Expected Values and Positive Operator Value Measurements in Parallel Repetition of Anchored Multiplayer Games. We're going to begin again, as we do typically for different types of presentations, by recalling a few facts and how this actually demonstrated how we were further demonstrating how there are various different aspects between multiplayer anchored parallel repetition and ordinary multiplayer parallel repetition. And again, one can recall that in the last presentation of this series, I spent quite a bit of time also describing how this big O notation corresponding to the computational complexity, it's relating to the fact that there's some type of uh, parameters and some ratio parameters which are appearing in this big O function, which is determining and communicating the computational complexity with regards to different expected values of interest. And in particular, what we usually do when we're looking at formulating expectation values of some norm, like we've been describing throughout these past couple of presentations, is that we're looking at tensor products of unitary transformations or unitary operators. And then this basically allows us to determine whether within or without the presence of anchoring questions from the which represent modifications to the quantum correlations and ultimately also to the questions that are originally distributed to each one of the players and participants from the referee's probability distribution, how this is actually really central towards establishing many of the types of arguments that I've been describing, namely, the viewer can recall those three main results that I described, in which we first began with the system of expected values. And then in the previous presentation in this series, I really drew his or her attention to basically how the how this relates to systems of expected values and systems of expectations, and how basically by starting with a more simplified system, one can look to introduce normalization factors or even twiddle quantum states, which is basically the same thing as the original quantum state for different strategies that players can use, but actually introducing some normalization, namely a normalization in the state itself. And in particular, for this case, we're seeing that we're considering a three-player setting because the support of the expectation value and hence the support of the underlying probability measure for the expectation is given by X, Y, and Z. And what we're doing, and we're trying to communicate with this with an inequality of this type of form, is that we're taking the norm of a difference between two quantum states where the first term, which is used in the decomposition for these two terms, which are appearing in these two individual quantum states that we're subtracting from each other and taking the norm of, and then taking the expectation of that we're saying it's equal to some big O function, which again, it's having this complexity theoretic related interpretation, is given by the fact that we're anchoring all of the questions from the referee's probability distribution. So it's pretty much like if you'd like, or what interpretation of it is basically relating to the fact that we're trying to break correlations and introduce as much dependency breaking or a quantization or a quantum version of the of this classical version of symmetry breaking from the works in from my works in statistical physics that I was using at the very first presentation of the series to try to motivate why dependency breaking has connections with and can be viewed, in fact, as a type of symmetry breaking. But obviously a quantum version because we're dealing with quantum versions and or quantum correlations in these types of states that we hope can impart some computational or algorithmic or even algorithmic perspective quantum advantage. And again, we're also describing how the main, I guess the main upshot we could say is that these results for these complexity theoretic related results are allowing us to conclude that there's some desired decay of the optimal value provided by Bavarian, Vidic, and Ewan, in which they describe how performing parallel repetition little n times for the anchored game, hence anchored parallel repetition little n times, is upper bounded by this exponential, where the power of the exponential is minus times, again, we had described these product of factors, namely the fact that this little c represents some strictly positive universal constant depending upon the game, Alpha represents the anchoring probability. Epsilon represents another sufficiently small parameter, as well as little n represents the number of rounds of parallel repetition, and this denominator or this numerator is normalized within the power of the exponential by some little s term, which is given in terms like how we've been describing the maximum between the logarithm, the natural logarithm, and the natural logarithm of the product of the questions that are distributed to each one of the players in the anchored game with one. So we're taking a maximum of whatever these quantities is the largest, which is serving as a normalization in the power of this exponential. In addition to the fact that we also have a prefactor term to the exponential, which is given by 4 over epsilon. And this type of, again, this type of expression for the uh, for the for parallel repetition of the anchored optimal value is really helpful because I'm going to be establishing more types of comparisons through a type of adaptation or kind of similar type of expression, which demonstrates how, again, like I've been describing at the end of the previous presentation, the third presentation of the series, it's really helpful to establish correspondences maybe through either two-player games or two-player games and multiplayer games, like I'd originally done in one of my works that's been under peer review for several months now, like 6 months now, in which I was establishing connections between XOR, XOR star, CHS of N games, and FFL games, and trying to basically compare and contrast these types of two-player game theoretic settings and how this is actually a very a very beneficial and a very helpful type of mindset to have even when we're looking at anchored parallel repetition besides ordinary parallel repetition. And the viewer will also recall that we had described the delta multiplayer threshold appearing in the three complexity related theoretic results at the end of the last presentation of the series. Namely, we're looking at this normalization in little n, namely the number of rounds of parallel repetition of the multiplayer game under anchoring. And what we were describing this parameter as, which is directly entering into play as one of the parameters that we're having in the big O function in the numerator, because we're always taking some delta multiplayer term and we're normalizing this in the big of O function for these complexity theoretic results that we're using to establish some type of desired optimal decay of the anchored or some desired exponential decay of the optimal value under anchored parallel repetition, because this type of expression is looking at the cardinality of all coordinates, namely, what is the total number of instances or rounds of parallel repetition across the questions that all of the players respond to, which are drawn uniformly at random from the referee's probability distribution, as well as given by the fact that we're looking at the natural logarithm of the absolute value of the product of the cardinality script q sub I for over the number of players, corresponding to what is the product of the cardinalities of the questions which are distributed to each one of the players, plus the log of 1 over the probability of winning across all the coordinates. So namely, we're looking at each one of the questions from one of the players from script q sub 1, script q sub 2, all the way up to script q sub big N. And we're looking at basically across all of the coordinates, namely across all of the instances of parallel repetition, whether there's a sufficiently good or sufficiently high winning probability for being able to satisfy the referee's scoring predicate and hence to win the game. And so, sorry, my computer is lagging a little bit. And so the cardinality of the coordinates can be identically expressed, like we also describe, as a union over the number of such coordinates for each I. So this is just basically a union where little I is ranging over the total number of players. And also, relatedly, the natural logarithm of the product of the question set is related to the delta multiplayer threshold, again, like we've been describing, just namely the natural logarithm of the product of the question set, which are distributed to each one of the players. And again, at various points in different points in I guess my career, we could call it, or even across different venues and conferences I presented at, which are on my YouTube channel. I've really always established comparisons between information processing tasks and quantum algorithms and more of an algorithmic type of perspective, because after all, a lot of the computations which are using for information processing tasks are still inherently rooted in terms of performing time evolution in the very same types of quantum circuits that say someone can be able to program in Qiskit from IBM, the open source package offered from IBM, or even Cirq from Google, which is what I primarily started out with in terms of programming noiseless quantum simulations, because it's really just demonstrating how this type of quantum circuit, which I'm providing on the slide, it's exhibiting 18 input ports and 18 output ports. And each one of these input ports, which is exhibiting each one of the registers or each one of the wires across which we can perform time evolution on qubits for, say, some whatever your favorite, whatever the viewer's favorite quantum computer is, can actually be used to basically perform time evolution from A of X and A of X dagger operators, as well as U and twiddle U, which are representing different different time evolution and different representatives of solutions, say for the Kamasa-Holm partial differential equation, which is one of the 15 partial differential equations that I had presented on this conference at, and just basically describing how there's some maybe potentially, hopefully, there could be some type of maybe polynomial advantage in terms of being able to add noise while still being able to run this quantum algorithm of interest in polynomial runtime or in polynomial time, which is, again, it's indicating a type of polynomial complexity, computational complexity, that is. And the POVM system, like we've been describing, is very much bridging the interpretations between quantum physics and quantum information theory in discrete probability, because what it's, after all, what it's allowing us to do is that we're looking, as the viewer can recall, if he or she saw the previous presentation of the series, we were describing several system of expectation values in motivating how maybe one can change the support of the question set for different expectation values, and how this is ultimately relying upon the, or relating to different types of probabilistic computations which we can have. And again, I was trying to underscore and make apparent for the viewer that as far as positive operator value measurements go, we can define each one of them for each one of the big N players, and how this actually factors into some of the computations which we're using for the second complexity theoretic result before we're finishing up the arguments with upper bounding another system of expected values with Pincer's inequality, is that we can just pretty much substitute the presence of probabilities that are appearing in norms of differences of probabilities that we're taking the expected value under, and pretty much we can instead insert in place the positive operator valued measurement. And again, given all of the types of descriptions of basically tensor product representations and taking tensors of or taking traces of operators of tensor products of operators, it's really not too surprising, because it's actually very helpful, because it establishes more of a concrete type of connection and similarity between probability and actually what is the expected winning outcome under anchored parallel repetition. And so I wanted to reiterate the concluding slide from the previous presentation, because it pretty much serves as a great, I guess a great starting point for this fourth presentation before I'm having the overview presentation in the last presentation of this series, for basically continuing to reiterate some of the points which we have been discussing, and how I'm going to basically tie all of these points together in the fourth presentation of the series. And that is, we further described anchored parallel repetition, and central to our approach are the objects relating to systems of expected values, normalization factors, quantum states corresponding to dependency breaking variables, in the fourth item, comparisons between time evolution of quantum circuits for variational quantum algorithms, through the example of the quantum circuit, of the portion of the quantum circuit that I provided for the viewer for the Kamasa-Holm partial differential equation. And altogether, we concluded the third presentation of the series with basically, I guess, the forthcoming arguments and discussion that we would be having in this presentation of the series, with regards to continuing to describe how complexity related upper bounds and the three main results are obtained, and furthermore, how this can also be related to the rate of exponential decay of the multiplayer optimal value under anchored parallel repetition. And so again, I just wanted to again describe starting a little bit from a ground zero again, so to speak, as I've done in different parts of the series to describe the Frobenius norm and how this relates to some two-player game theoretic responses. And then we're going to be able to pivot back to multiplayer and anchored parallel repetition with some additional aspects of arguments and computations that I've done in previous papers recently from this year, from a couple of months ago. And so that's just basically given the fact that if we're looking at the Frobenius norm of some matrix A, it's identically equal to the square root of the summation over the number of rows little m and the number of columns little m of the absolute value squared of Aij, namely each one of the entries of the matrix, which can itself be expressed in terms of the square root of the trace of the Hermitian complex conjugate of the matrix multiplied by itself. And why multiplayer games and the two-player games are actually really helpful is because there are a lot of other connections rather than what I've just been describing in terms of what is the expected rate of decay of the optimal value, because it shouldn't surprise the viewer that in previous presentations from this year on my channel, focusing on quantum information processing and quantum information theory, I've really been drawing a lot of attention to the fact that the rate of decay of the optimal value, it also has a lot of connections in terms of what are the types of error bounds and maybe potentially generalizations of error bounds under anchored parallel repetition or under ordinary parallel repetition. And this is given by the fact that the optimal value is also important because there are a collection of suitable linear operators which allow us to construct other types of inequalities which are related to error bounds and even to generalizations of error bounds. And this is given by the fact that we can see that in this case, we're looking at maybe multiplayer XOR games because it's really great to have this type of discussion, this type of interaction between two-player games as the simplest case and multiplayer games as adding more layers of complexity to the mathematical arguments and to the types of computations that we would hope to be able to perform. And this is given by the fact that we're looking at the tensor product of the suitable linear operator XOR, which is given by the mapping where the preimage of the mapping is given by a tensor product over big N copies of this Hilbert space C raised to the 2 to that has dimension, sorry, that has to the Hilbert space, the complex valued space that has dimension 2 times the floor of little n over 2, which is mapping into a tensor product between the number of players for I between 1 and big N inclusive of C of DI. And pretty much having this type of expression for the tensor product of suitable linear operators, like I've described in previous presentations on the channel, it's really helpful because we're able to quantify some type of anti-commutation relation with regards to these operators and how that's actually reflecting, in some sense, the expected impact on the optimal value that one would hope to obtain through error bounds and generalized error bounds. And we can see also relatedly that on the second slide in this slide, or the second line in this slide, it's really helpful because we can look at also performing the wedge operation, namely parallel repetition of these suitable XOR linear operators, which is just given by, with regards to the preimage of this mapping, performing parallel repetition amongst individual copies of the Hilbert space, as well as also under the image of the mapping in the image, actually continuing to take the parallel repetition operation through this wedge operation of each one of the d sub i's, the C d sub i's, which we had introduced in the tensor product of these suitable linear operators in the previous slide. And then this is just pretty much to say that also for parallel repetition of the XOR game, we can also look at performing just the parallel repetition operator in the dimension of each one of the Hilbert spaces and being able to map into some complex value space that has dimension where it's given by the parallel repetition operation applied to each one of the dimensions across corresponding to the potential answers that each one of the players can provide in response to the questions drawn from the referee's probability distribution, as well as even for the FFL game, which differs from the other suitable linear operators on the slide in the sense that we're performing parallel repetition of a two-player game instead of for the multiplayer games, is given that it's just two instances or one instance of parallel repetition, which corresponds to two Hilbert spaces in the preimage and the image of this mapping. And so altogether, the 3XOR suitable linear map can be expected to take this following form, namely a very straightforward generalization, namely where each one of the Hilbert spaces, which is appearing in the tensor product in the preimage of the suitable linear mapping, is given in terms of being raised to 3 to the floor of little n over 3, where obviously the 3 isn't corresponding. Its significance is that there are just 3 participants, which is being mapped into a tensor product of 3 Hilbert spaces with respective dimensions d sub a, d sub b, and d sub c. And the inequalities associated with the 3x or T map, like we've been describing, these suitable types of operations which I'm going to describe, are related to optimality and decay of the optimal value, and which can impact the types of generalized error bounds that one would hope to construct, which again is going to be related to, as I'm going to describe, multiplayer anchored parallel repetition, is given by the fact that we can look at it as the following. Namely, in the three-player settings, the accompanying operation T sub prime, which is identically equal to the 3XOR suitable linear operator, has the following collection of actions. Namely, we're looking at the norm of basically a subtraction of two operations of tensor products, which are multiplied by kep psi 3 of XOR. And we're looking at basically some suitable type of normalization from the 3XOR game or the 3XOR suitable linear operator, which is given by just basically permuting the position or changing the position or interchanging the position in which the suitable linear operator T prime appears. Like we can see, namely, for the first expression that's given in the slide for the first norm, we're looking at T sub prime occurring first, whereas in the second inequality, or the second norm in the second slide, or in the second line, we're looking at T sub prime occurring in the second place. And finally, for the third line, T sub prime occurs in the third place. And so this is just basically given by the fact that that intertwining relation, which again can be realized as a type of manifestation of the Heisenberg uncertainty principle, because we're basically interchanging the order in which certain operations and certain operators are being applied in this quantum state that we're trying to act upon with either the kep psi 3 XOR, namely the optimal strategy for the 3 XOR game, is given by the fact that we're applying some twiddle operation, which can just correspond to maybe switching the indices or performing some transformation on the indices of the tensor that the second player Bob is using, or even maybe looking at even introducing some novel type of normalization, like how we had described from the system of expected values in the previous presentation of this series. So this is just really demonstrating how different types of inequalities and making use of common tactics for actually being able to quantify some type of anti-commutation relation or some type of interchanging or intertwining relation. It's something that's of great interest to formulate, and that I've definitely formulated across quite a few of my works in statistical physics and quantum physics alike. And so altogether, the system of inequalities allow us to relate to the formulation of bounds given of the following form. So this is one of the precursors that's important for us to consider when we're looking at error bounds and how this is actually relating to the different types of computations that we would like to perform, which are inherently dependent upon the optimal value, and how this will relate to the anchored parallel repetition of the optimal value that I'm going to provide at the end of this presentation. And in particular, again, it shouldn't surprise the viewer that, again, we're just considering the multiplayer NXOR settings. So just the XOR game with big N number of participants for this particular multiplayer game theoretic setting. And we're looking at upper bounding the Frobenius norm, which is why I introduced it at the beginning of the first one of the earlier slides of this presentation of the series, because basically we're taking the Frobenius norm of this quantum state for the XOR game. We can see that we have a kep psi and XOR for all these types of inequalities. And we're having, in fact, a family of inequalities, a collection of inequalities, because in the first inequality, we're looking at the product between the number of players for the tensor A sub j sub I of I, namely where we're performing some type of different index or for the superscript of this tensor, which is corresponding to the responses from the first player, Alice, or whatever the first player's name is, as well as in the second inequality with this connection, instead in the place of where the A tensor was appearing in the first inequality for the NXOR game, we're having an identity in moving the position of the A tensor in the next position in the next entry of this tensor product of operators. And we can perform this type of analogy, so on and so forth, for arbitrarily number of players, for being able to perform some type of computation for the upper bound of the Frobenius norm, which is, as I'll demonstrate to the viewer in more detail in this presentation in this series, actually having some connection and some resemblance towards optimality and approximate optimality, as well as being able to generalize the error bounds that which are of interest. And in a two-player setting, the FFL game is given by the fact that we can again see this type of anti-commutation relation, which is related to what I demonstrated in this slide with the suitable linear operator for the T XOR map, or for the 3 XOR T map, from the perspective that we're just basically looking at for all I or for all j not equal to I respectively for the first and second inequalities of upper bounding the Frobenius norm, in which we have again the square root of some sufficiently small parameter epsilon FFL, as well as the Frobenius norm of the FFL suitable linear operators. So basically, one can define classes of suitable linear operators, and how this actually relates to optimality again is that we're basically seeing what would be the invariance or the expected change for the action of this suitable linear operator when we're interchanging the position, and at the same time, simultaneously, as we can see in the first inequality of the slide, performing some twiddle operation to A sub I. So basically, we're keeping this type of ordering the same, but for the tensors which are appearing in some tensor in the tensor product of operators, we're performing some transformation on these components to account for the fact that we're interchanging the order in which the FFL operator is applied. Okay, and so the objects associated with parallel repetition are given by the fact that, again, we can look at script q sub 1 of 1 of 1, which is namely the set script q sub 1 of 1. So which is given by the set of questions distributed to the first player of the expanded game in the first instance of parallel repetition, as well as just relatedly in the next line below it, the set of questions distributed to the second player of the expanded game, as well as being able to perform parallel repetition, namely parallel repetition between these two question sets corresponding to the first and second players of the expanded game, as well as in the fourth object, which is defined on this slide, parallel repetition of the question sets from the first player of the game for an arbitrary little n number of rounds, as well as just introducing the symmetrized game tensor, which the viewer will recall in a previous presentation in this series. I define this as some higher dimensional object, which is given by a matrix representation of the original game matrix, in which we have zeros along the diagonal and the conjugate transpose, and if I remember correctly, the minus conjugate transpose along the anti-diagonal of the game matrix. And pretty much also we can define some type of, it shouldn't be surprising that we can define some symmetrized game tensor for parallel repetition of the expanded game. And altogether, this is underlying semi-definite programs and dual semi-definite programs, where the particular notation which I introduced for dual objective functions for semi-definite programs, for dual semi-definite programs, is given by y subscript of q. And so parallel repetition of answers that players provide in response to the referee's question can be phrased through quantum states of the following form. Namely, we're looking at maybe some collection of players, I sub 1 and I sub 2 corresponding to just maybe Alice or Bob, or just two-player games with only two participants, or game theoretic settings with two participants, and how this is pretty much relating to the fact that we can perform, even for the two-player case, an arbitrary number of parallel repetitions in the quantum states, the Bra and the Ket states, which are provided in this slide. They're basically given by the fact that it just admits a very straightforward type of decomposition with respect to the wedge operation, namely with respect to the parallel repetition operation, just basically component-wise amongst each round of parallel repetition. And positive semi-definiteness is coming into play because, as I discussed in a presentation, in presentations, and in a series from May of this year, when my first paper for my first preprint, my first paper and project came out on the archive, I was describing in those presentations how positive semi-definiteness is actually also very related to basically notions of exact and approximate optimality. And this was given by the fact that in that first paper from this year, one of the results which I had in that paper, Theorem 1, was describing how basically you can make use of a positive semi-definiteness condition again, where we described, the viewer will recall that when we were describing semi-definite programs and dual semi-definite programs, that basically the partial ordering was taken with respect to some curly inequality, which is indicating that we're taking the ordering with respect to the positive semi-definite cone. And this is given by the fact that we're looking the subjective y sub I, e sub I, where e is just related to some type of transformation of the game matrix that we would like to study, and we would like to determine how just basically this objective multiplied by e sub I minus the symmetrized game tensor would just basically differ, and whether that is always positive semi-definite, which would in fact indicate whether there is some type of expected advantage for players when they're using quantum entanglement and other aspects of quantum information. And again, in the second line here, we can see again that we're recalling that we can just look to take the supremum of G expanded times the primal feasible solution. Sorry, that's a typo. It should be Z, the primal feasible solution should also correspond to the expanded game. But basically, we can perform the parallel repetition, the wedge operation amongst however many rounds of parallel repetition for expanded games and generalizations of expanded games, which was originally the type of game and the type of quantum framework which Bavarian, Vidic, and Ewan had considered in their preprint or in their paper in the reference I've been describing pretty much since the beginning of this series. And again, it just shouldn't come as a surprise that we can formulate a dual semi-definite program associated with the original semi-definite program like we've been describing at a couple of points from this presentation in the series, from these presentations in the series, from basically interchanging an infimum with a supremum or a supremum with an infimum, as well as interchanging just basically the objective and changing at the same time the constraints which we're enforcing on the dual semi-definite program. And so again, one can recall that now I want to bring things more full circle, so to speak, in terms of establishing more of the multiplayer anchored parallel repetition interpretation and how that can be related again from these more simple concepts for two-player or multiplayer XOR games, or maybe two-player FFL games and parallel repetition in all these types of variants of quantum games, and how this basically relates to the connection between the complexity theoretic related results and the decay of the multiplayer anchored value. And namely, that's given by the fact that basically we look at twiddle of E sub gamma sub I, which is given as some type of generalization of the original simpler system of expected values that I provided for the viewer in the previous presentation of the series, because we're inserting these gamma sub I factors, and we're even taking product of gamma sub I factors. We'll recall that each one of these gamma sub I factors is defined in terms of a ratio of just basically norms where either we're anchoring certain questions or we're anchoring all of the questions, like we had described in the previous presentation of the series. And this is altogether, again, relating to the POVM system that we provided an expression of earlier in this presentation of the series, because we're just basically looking at being able to upper bound with this complexity-related theoretic result, some POVM, script POVM of E system, namely the fact that we're taking expectations of probabilities and also of positive operator valued measurements, and how this is relating to the decay of the expression for the optimal value that I'm going to present under anchored parallel repetition. And so Pinska's inequality system is given by the fact that, again, we have been describing how this relates to the theorem 3 or the third result, which is relating to some big of O upper bound, namely some complexity theoretic upper bound for Pinsker's for the inequalities, which we're going to be able to upper bound with Pinsker's with arguments from Pinsker, which is just basically relating the L1 norm between two quantum states in terms of an entropy. And this is given by the fact that we're looking at expectation, which is taken with respect to I, but at the same time, we're also having two more remaining expectations that are nested within the outermost expectation for each one of the components in the system. Because again, we're looking at an instance of dependency breaking big R sub minus I, conditionally upon the fact that we're looking at the fact that, or, conditionally upon the fact that the players can win across all coordinates big C. But at the same time, we're introducing an expected value, which is actually taken with respect to the probability measures of a product support, namely the product over the question sets for each one of the big N players. But we're actually looking at something a little bit differently that we're looking at with regards to taking the norm, because basically we're looking at one minus, these boldface one, two, or up to boldface of n terms, which are corresponding to some instance of dependency breaking variables from quantum circuits, from registers, basically of quantum circuits like what I had presented, similar to basically the quantum circuit that I was performing time evolution on for variational quantum algorithms, namely the fact that each one of these registers, E sub 1, E sub 2, all the way up to E sub big N, is just exhibiting different types of registers that players are using when they're basically playing the game, and how this is informing the squares of the L1 norm or the square of the absolute value norm that we're upper bounding for this final inequality in the third complexity theoretic related result before we're obtaining the desired result on the decay of the optimal value under multiplayer anchored parallel repetition. And it shouldn't come as a surprise that, again, like we've been describing and reiterating at various points of the presentations in the series, is that unitaries are very important for each player. And namely, we make use of the collections that we have unitaries corresponding to the first player, script u sub q1, which is identically equal to script u sub 1, all the way up to script u sub big N, corresponding to the nth question that's distributed to the player from the referee's probability distribution. And dependency breaking unitaries also come into play because we're just pretty much adding in additional structure to the unitaries which were provided on the previous slide, given by the fact that we can look at instances of dependency breaking away from some position I. So the viewer will recall that when we were describing dependency breaking, we were first describing it occurring at some position I amongst all of the coordinates, namely amongst all the instances of parallel repetition for some game. And then we were actually describing how we can also look at dependency breaking away from this coordinate. So it's pretty much exhibiting what are a lot of the structures and the forms of the inequalities, and just basically the system of expected values that I provided for the viewer, because we're basically looking at either maybe dependency breaking at one single isolated location, namely one instance of parallel repetition, or maybe multiple instances of parallel repetition away from some fixed instance within the set of all coordinates big C. And to upper bound the POVM system, one can continue appealing to interpretations between traces of tensor products and probabilities, namely just given by the fact that before we're taking the expectation of each one of these components, which the viewer will recall was given by PO script POVM of E. If we're just looking at the system described by script POVM instead, we're looking at the norm between the probability of some probabilities multiplied by some POVM minus another probability, as well as just generalizing this type of expression and this type of norm for however many participants there are in whatever multiplayer game we're interested in considering. In an intermediate system that is coming into play to upper bound the Pinsker's inequality system is given by the fact that, again, we're describing how we want to ultimately relate to the fact that we can perform computations with Pinsker's inequality and be able to maybe establish some type of correspondence in terms of computations with entropy. And this is given by the fact that, again, this intermediate system for Pinsker's inequality is given by a normalization of 1 over the number of players for each one of the expectation values, given this instance of dependency breaking, as well as just given by the fact that we're taking a summation of, or just taking the expected value of just the relative entropy of the dependency breaking state away from position I for the first player and the second player and the third player, and so on and so forth between the big N minus one player and the nth player. And I also wanted to provide a couple of sets of conditions, which are again really demonstrating how a lot of very similarly related quantities to what we've been describing as the parameters, which are entering into the big of O function, namely the delta multiplayer and the multiplayer anchoring probability, are basically coming into play. Namely, the fact that in this one lemma, which is a pretty straightforward and direct adaptation of a result which is given in the paper that we've been discussing for non-local anchored parallel repetition due to Bavarian, Wittig, and Ewan, is given by the fact that they basically establish several types of instances and inequalities, just basically describing what are the parameters which enter into play for the big of O function for the computational complexity. And in fact, we can see that in the first instance, the first item, the average of the probabilities of sampling dependency breaking variables is strictly upper bounded by a fraction delta multiplayer by square root of a fraction of delta multiplayer. It's given by the fact that this upper bound, or this power to which we're raising this delta multiplier parameter, is dependent upon the number of players big N by divided by 300. So basically this is relating to some type of generalization, because the viewer can recall that there were types of parameters that the powers to which these types of parameters were raised in the two-player setting was relating to like 1 over 16 or 1 over 8 and those types of quantities. And even for the multiplayer anchoring or for the two-player anchoring probability, it was raised to numbers such as 5/4 and so on and so forth. And how pretty much you can not only make use of their computations for being able to determine how the power in which the multiplayer and alpha multiplayer, namely the multiplayer threshold and the multiplayer anchoring probabilities, would change, but also how this is basically relating to actually how this would impact overall the decay of the optimal value. And also from another perspective, illustrating what would be the range of parameters that one would expect to be able to find from error bounds, namely certain whether there are certain constraints on within maybe an arbitrarily large combinatorial space of strategies that players could make use of for some type of prospective quantum advantage. But besides the first item, we have the second item, which is similar to the fact that we're looking at a similar expression which is given in the first item, but at the same time given by the fact that instead of having the probability of sampling an instance of a dependency of a multiplayer dependency breaking variable, we're looking at instead some instance of symmetry breaking, while just basically leaving the rest of the components, the conditioning and the support of the probability measures the same, and we're not changing those. So you can basically see like how these types of probabilistic statements, again, it's really describing and really hitting home, so to speak, or really providing all of the type of justification with regards to the complexity theoretic related results, because we're either looking at sampling some instance of dependency breaking or sampling some instance of a dependency breaking variable within the multiplayer set of all dependency breaking variables. And the last two items are even related to each other for a similar type of reason, in that we're looking at the presence and under the influence of anchored parallel repetition, or just anchoring each one of the questions and determining how repeating this process indefinitely would actually impact the rate of decay, the expected rate of decay, whether it's exponential or not for the optimal value. And a second set of conditions is given by the fact that the following inequalities provided in the previous item also relate to the following probabilistic statements. So just basically, as we're saying in the first item on this slide, conditionally upon winning across all coordinates, the probability of sampling R, namely some instance of dependency breaking, given any script Q sub I, namely given any set of questions that are distributed to the players from the referee's probability distribution, is upper bounded by a fraction like we've been describing of delta multiplayer normalized by alpha multiplayer, namely the delta multiplayer threshold normalized by the alpha multiplayer threshold, where we can see each one of these expected values within this system is actually has the same and identical complexity theoretic upper bound, namely the upper bound given by the square root of the delta multiplayer parameter raised to the big N over 300 normalized by the alpha multiplayer parameter raised to the N plus 1. And we can see that just basically on all these other types of expressions on the side, we can make use of these types of arguments for very similar computations with regards to what is the threshold or what are the actual, which is ultimately determining the parameters which are entering into play for the big O function for these complexity related theoretic results. And the computations for upper bounding the system of expected values in the first complexity theoretic result, namely one can say the system of expected values that is closest to the first system of expected values for the simplest situation that I provide in the previous presentation in this series, is given by the fact that we're having basically the square root of a norm squared computation where either we're looking at, say, twiddle up psi of some state minus twiddle psi of another state, which is altogether allowing us to upper bound each one of these quantities just basically by this big O function where instead of the square root, which is appearing in the square root of the square root, which is appearing in the complexity theoretic upper bound for the POVM system, this parameter, which is appearing in the numerator, does not have any square roots, but nevertheless, it's still normalized by the multiplayer anchoring probability raised to the big of n plus 1 power. In the intermediate POVM systems should also not be a surprise that they're very important for us to consider because for upper bounding POVM E, script POVM of E, namely the system of expected values of positive operator valued measurements, we look at the intermediate systems, namely the system prime and the system prime prime, where we're looking in the first prime system just the POVM minus some probabilities, namely the probability of sampling some answers for the players given some instance of dependency breaking for a wide variety of multiplayer game theoretic settings, as well as in the script POVM of E prime prime system, we're introducing expected values and taking expectations of the probabilities and just basically the POVM minus probability terms, which are given in the first intermediate system, which is given on the slide. And an adaptation of the 3-player bound to a 4-player bound is given by the fact that in the same way that we had described how there's a 3-player bound, we can also adapt the arguments to conclude that given the expectations supported over Q1, Q2, Q3, and Q4, also given the fact that we have two other expectations which are taking an expectation over all the coordinates in addition to taking an expectation of an instance of dependency breaking conditionally upon the fact that we're winning across all coordinates is given by the fact that it has a complexity related theoretic upper bound of namely of delta multiplier raised to the 1 over 100 normalized by alpha to the multiplier raised to the 4th power. So it's just pretty much demonstrating how this type of more simple example can be used to build up larger systems of computations, probabilistic computations from discrete probability, in fact, and how this is relating to our goal of the optimal value. And so now I just wanted to end up the 4th presentation of the series before we go to the 5th presentation of an overview with actually the expression of the anchored optimal value under parallel repetition, which is given in my paper, in my upcoming preprint, as theorem 4, which is given by the rated decay of the optimal value under anchored parallel repetition. So basically what we want to do is that we want to fix an S multiplier parameter, which is given by, again, like we've been describing, the maximum of the natural logarithm of the products of the natural logarithm of the cardinality of each one of the question sets with a second parameter alpha multiplier, which is determined to be between 0 not inclusive, but potentially could be 1 inclusive for corresponding to a multiplayer alpha anchored game G, as well as two other strictly positive parameters, namely epsilon multiplier and a universal constant C multiplier, where this last parameter C multiplier is given by the fact that it lies strictly between 0 and 1 over big N raised to the 2 of big N log of E. And as a result, given these parameters that we can fix, the decay of the multiplayer optimal value, omega multiplier of G, under alpha anchored parallel repetition, which is given by omega multiplier of G anchored raised to the tensor power to the tensor project of little k times corresponding to k rounds of parallel repetition, satisfies this form, namely it's upper bounded by some exponential, 10 divided by epsilon multiplier multiplied by an exponential, where we're having a lot of these similar parameters which are coming into play from the result due to Bavarian, Vidic, and Ewan, namely, they were having a minus C multiplier, the multiplier anchored probability raised to the 20n plus 1 power, the epsilon multiplier probability raised to the 20n power. We're having a copy of n because that's corresponding to the total number of participants in the game, as well as just basically the S multiplier parameter, which is normalizing the power of this exponential. And so the conclusion that I wanted to end up the fourth presentation of the series with is that we established connections between operator value measurements in addition to how previous work of the author from me for generalizing error bounds can be applied to other game theoretic settings rather than only for multiplayer games. And this is all to say that parallel repetition under anchoring has distinct impacts on the decay of the optimal value of a game in comparison to the effect of ordinary parallel repetition. And in the concluding presentation, or the concluding section, the next presentation of the series, we're going to provide an overview of arguments for making connections between two-player and multiplayer games and just describe, briefly different types of points which we have been reiterating for obtaining the estimate which was provided on the previous slide for the decay of the anchored optimal value under parallel repetition. And thanks for watching.